Hello all, as we continue our look into circular functions. In this video we're going to start to bring together a bunch of the ideas from previous videos, ideas of symmetry, exact values, memorizing exact values, all those things. We're going to bring them together, and now we're going to look at finding the actual solutions of trigonometric equations. Now, why may we want to find the solution? Well, the most obvious case is, say we are trying to graph a certain function. In this case, we might be trying to graph y is equal to 2 sine x minus 1. And we want to find the x-intercept. Well, when we want to find the x-intercept, we know that we let y equal to 0. So we've done that here. And then we can start rearranging this. Just solving like any other sort of function or equation. We just solve by applying inverse operations, and we get to something like sine x is equal to half. And if we remember our exact values, okay, and what is this saying? Well, this is an x in here. We could also think of that as theta. Anything inside a sine, cos, or tan is an angle that we're putting in here. Is what angle, in this case the angle is technically called x, gives us, and sine, so gives us a vertical component of half, or a y value of half. Now, we don't care about what the x coordinate is in this case. We just, what angle will give me a y coordinate or vertical component of half, and if we remember our exact values, that happens to be pi on 6 or 30 degrees. And that's what we get. Then we've just solved and we've figured out that that is an x-intercept. A thing to note here is that this is just the first x-intercept. Because if you just think of any sine graph, we know it goes something like that. And we technically have one here at 0, 0. This one here for this equation is technically going to be at, what did we just figure out? Pi on 6, but we know there's going to be another one here later and another one here later. And we've also ignored that there's this sort of minus 1, which, if you recognize our functions, anything add or subtract on the end is like a h value. So technically this graph would actually be and then something like that. There's that first one, pi on 6. We're going to have more intercepts. So a lot of this video is going to be about, one, finding this first one, because we need to find this first one. You need to get that correct, because if you get this one wrong, you're going to get all the rest of them wrong. So this is where having really strong memory of the exact values, or coming up with a process that you can find the exact values correctly every time, that's really important. So it turns out for this equation, if we wanted to graph it, we've let y equal 0, we've solved, used our exact values. We know that x is going to be pi on 6 will give us our first time that y is equal to 0. This first solution, from now on, we're going to call the reference angle. It's really important. We're going to use that terminology a lot. Right here, so just a quick practice, some example, find the first solution. So we're just caring about pretty much the one that's going to some form of calculation that we think's the first obvious one that comes to mind. So we've got 2 cos x minus root 3 is equal to 0. So we just start applying inverse operations. So I'm going to add root 3 to both sides. I now get cos x is equal to root 3 on 2. So this is again essentially saying some angle, what is that angle? Called x, and I want the horizontal component now, and I want that to be root 3 on 2. Because it's doing cos. What angle is going to give me that? X, well, x is going to be root 3 on 2, that's the largest horizontal, so that will also be pi on 6. And that's our first solution. Do the same for example B, we just apply inverse operations like normal is equal to 2 root 2. Sine x is equal to 2 root 2 on 4, so we get sine x is equal to root 2 on 2, simplifying. So what is x going to be equal to? It's asking for the vertical. What angle would give me a vertical component of root 2 on 2? That's the mid angle. That's 45 degrees, or we know that as, or not 45. That's pi on 4. So that's fairly straightforward finding the first one, and you're going to have that down pat to get the rest of it along. So the thing is, like I said back here, if we keep sketching any sine or cos, it's this continuous wave that goes on and on and on. So we're going to have more and more solutions. So where do these come into it? Well, this is that idea, recognizing that, yeah, well, there was this angle, x, in the first quadrant, but there's going to be angles in all other 4 quadrants that may also give us the same required horizontal or vertical component, or this required x or y value. So if we want to convert an angle that was working in the first quadrant, we can use this following table here to find the symmetrical angle, or that's symmetrical. It's using the symmetry from a previous exercise. Where would that angle be in all the other 4 quadrants, or the other 3 quadrants, that would also make that work? So, for example, this one here, we had our first one as pi on 4. What is the matching angle in the second quadrant? Well, we could imagine going all the way around to pi, and then coming back our angle, which was pi on 4, and that's what this is saying. Go to pi, come back pi on 4, and that will give me, and we were doing in that example sine. Our first quadrant, that was my vertical component. That was the required vertical component. We could also get that exact same vertical component by going into the third quadrant. So instead of going to the second, I could have gone all the way around to pi, and then gone another pi on 4, and that vertical component there is going to be exactly the same. The only issue with this one is it would be negative down here. And we could find it here, but for sine anyway, in that quadrant, that's going to give me a final answer of negative. Now, in this example, we needed positive root 2 on 2. Maybe this original equation here was positive, so we would have gone through the exact same process, but that was negative, 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 and I needed a negative root 2 on 2. Well, the first solution that gives me a negative value of that is in the third quadrant. So there it is there. It's the pi plus pi on 4. So my answer would have been pi plus pi on 4 for the required angle. Gives me, what's that? Trying to work, that's 5 pi on 4. Is the first working one. And if I wanted to find the second intercept, I would note that, well, I needed a negative component. That means over here would also be completely fine. So in the first quadrant was pi on 4. In the fourth quadrant, that would be the same as going all the way around to 2 pi and then coming back pi on 4. And that's what that's showing there. So not only is 5 pi on 4 an acceptable solution, we would also take a 2 pi take away pi on 4, which happens to be 7 pi on 4. So that's the first solution that would work for if we started with a positive in there and then it became negative on the other side. But looking at symmetry, we would also know that 7 pi on 4 is technically a correct solution to, let me write this over here. Our question was sine of x. We eventually got it round onto the other side, negative root 2 on 2. 5 pi on 4 is a solution to it, but also to get that vertical component of negative root 2 on 2 in this fourth quadrant is fine. We could also think of, and it's not technically called this, we could talk about, what about the negative first quadrant? What if we rotated the other way? What instead of going this way, we went this way? Well, that would be a 0 takeaway x angle. And that would give me also a technically correct solution. If I said the angle was, if I just went negative pi on 4 that way, so I now get a third solution. That I might write over here just to write them sort of in numerical answer. And then I could also keep going all the way around to pi and then come back this way, and that's sort of in the negative second quadrant, going backwards. And what would that be? Well, I went to negative pi, but then added my angle. So I could have gone to negative pi and then add pi on 4, so that's the same as negative 3 pi on 4. That would also technically give me this requirement. That gives me the required vertical component of negative root 2 on 2. So turns out there's infinitely many answers. I could go around that circle 6 times if I wanted to. I could go to 6 times around, well, that would be 12 pi. And if we just think of our normal 4 quadrants, okay, and I want this, I could go around 6 times. I'm back at the start. Then I need negative, so I need to go around another pi and then another pi on 4. Pi, so that's 12 pi going round circle 6 times, plus another pi plus pi on 4. So that would be what, 13 and then pi on 4. That is also technically a correct solution to this. Now, you're not going to need to find 15 solutions. We're not going to ask you to go around once, twice, 3, 4, 5, 6 times or something like that. When we graph circular functions, you'll be given a domain. You'll need to work maybe just one rotation, the first 4 quadrants. That's a pretty common one, is just solving between 0 and 2 pi, so we care about the first 4 quadrants. Other times, though, you might be asked from negative pi to pi. That comes up a lot. So you need to be at least able to somewhat think about, what if I have to go backwards around the circle? Where would be my symmetrical equivalent angles? So let's actually apply that. That's a lot of drawing and writing and scribbling, but go back, pause, rewind, look at that picture, copy it down without all the scribble on it. In this table, you really need to understand and know what would they be symmetrically. And if you think about it geometrically as a physical picture, that should hopefully make it a bit easier. Rightio. So that's pretty much all what we talked about. If we took 2 cos x minus root 3 solved, we got our first solution as pi on 6. We would realize, well, there would be some symmetrical positions. What other angles would give me a cos value of root 3 on 2? Well, cos and we needed a positive. We need positive root 3 on 2. So I go back to this sort of diagram. That was my first angle there. That gave me the required one. I also needed, if I was down in here, if I went this way, that would work. Or if I went all the way around that way, that would work. So if I thought about going sort of all the way around, I went all the way around to 2 pi, come back. That's sort of my 4th quadrant symmetrical one. Then using my reference angle, my initial one is pi on 6. If I use that, another correct one would be 2 pi. Take away my reference angle, which is equal to 2 times 6, 12, take away the 1. That's 11 pi on 6. And that's what that shows here. So that's how you decide, do I want first, second, or third, or 4th quadrant, is looking at signs. In this case, I needed positive root 3 on 2. So cos is only positive in the 1st and 4th quadrants. So I'm only going to accept 1st and 4th, so I don't need to worry about trying to find the 2nd and 3rds. Rightio, so let's have a go. Find all solutions to the equation tan theta equals root 3 over the period 0 to 2 pi. Well, we know tan theta. For tan theta equals root 3, we know the basic solution to that. If we think of our table of values, tan gets bigger. I'm just 30, 45, 60. The first one is 1 on root 3. That one's 1. That's root 3. Because they get bigger as the angle gets bigger. So that's 60. 60 is the same as pi on 3. So theta must be pi on 3. That's my reference angle. There we go there. Pi on 3. That gives me a tangent. Draw it in. Of root 3. Okay. That's my first solution. We can also, that was our first quadrant, we can have solutions in the second, the third, and the fourth. Now we need positive pi on 3, so that actually rules out the second, and that rules out the fourth for tan. Tan is positive in the third quadrant, so I need to find what's the matching angle here. That's coming around here, pi on 3. Well, the next one is, of course, that would be pi plus pi on 3, which, first one, 3. Pi plus pi on 3 is 4 pi on 3. So there's my solutions. I could have found the one in the second quadrant, which was going round a pi. Let's actually write them all in, and then I can show you, because we'll be using this sort of process. So we have that one. We then have pi take away the reference angle. We have pi plus the reference angle, and then we have 2 pi take away the reference angle. That's the four. That's what these four are showing here. Reference, pi take away, pi plus, 2 pi take away. So we get, what's that? That's 2 pi on 3. We get 4 pi on 3, and then we get 5 pi on 3. But because we wanted positive root 3, we need to ignore what's in the second and the fourth quadrant, like I'm saying, so we get to ignore those. So that's solving equation and then finding for multiple solutions. Now that's for, unfortunately, easy trig equations, which is where it's just the angle is equal to something, tan or sine or cos of the angle. Now what happens when we start transforming graphs is that we get a whole bunch of information in here. We might be dilating, there might even be horizontal translations, there can be vertical translation stuff, well, vertical's outside the brackets, but what happens when we have sine of something more complex? And that's what this g of x is here is sort of representing, is there's some other function. I guess you can say that there's a function inside that sine. We're applying something to theta, it's not just theta itself. So we need to work with, when we're given our initial domain, we need to convert it to something called a working domain. Because when you solve the technical, what's technically going in the background is you might technically be going, let 2 theta equal a. So you can now write it as cos a equals half, and you solve for a, and then you're going to convert it back to 2 theta, and that's what's happening technically in the background. But when we're doing this sort of, I guess, substitution, while our original domain technically was related for theta, we've changed it to an a, so our domain's changing. And we call that change domain of what we're going to deal with, or what we're going to cross-check our allowed values, is this working domain. Now, it's pretty easy to find. You take your old domain, take the two numbers, and sub it into whatever is what we call g of x, this bit inside here. Just the bit inside. So in our case, g of x is equal to 2 theta. So I take 0 and I stick it in that and see what I get out. So g of 0 is equal to 2 times 0 is 0. I put pi in there now, so I'm going to put pi in, and I get out 2 times pi, so I get 2 pi. And that's my new domain. So I'm going to, when I solve this cos bit, because I'm technically doing this cos, what gives me half, and I'm going to write out values, I'm going to list all the values that work, I'm going to list here, that's what this is, listing values, they need to be in the working domain. And they will, by listing values that are inside the working domain, once we bring this 2 over this side, that will actually convert them back to inside our original. So that's our original, this is our working domain. And if you're a little bit lost here, that's okay. I'm going to go through some worked examples. I know the video is already at 20 minutes, so you can watch one. I'm going to do a heap of worked examples, so it's going to be a longer video, but it's there so that if you want to go through the multiple examples, or if you're really struggling, watch all the examples. If you're all over it, then watch the first one, and then that will be fine. So, I've got heaps of scribble here. I'm going to now get rid of a whole bunch of this. So, actually, I'll leave that there and working domain. So I had cos of 2 theta is equal to half. Well, this is asking cos of, well, something needs to give me a horizontal component of half. Well, that's something. This inside here technically needs to be, to give me half, we know from our exact values, that thing in there needs to be, or the angle that gives me a horizontal component is, get my brain, half, that's, oh, I'm blank. Smallest one, that will be pi on 3. Yeah, okay. So if I had written cos x is equal to half, you'll say, well, this angle to give me the horizontal component is pi on 3. So that's what we put here. Pi on 3. And we also know from our symmetry, in between our working domain's from 0 to 2 pi, so we'll accept anything that's in all 4 quadrants. For cos, it's positive in the first and the fourth, so we would find the fourth one, so that's our first quadrant. This one here is our fourth quadrant acceptable solution, and it's acceptable according to our working domain, is 2 pi minus pi on 3. We simplify them, well, pi on 3 stays pi on 3. 2 pi minus pi on 3 is 5 pi on 3. Once we've got this, because we're effectively 2 theta, well, now we bring the 2 over, just divide both sides by 2, and we now get theta is equal to pi on 6 and 5 pi on 6. And if we compare these values, now that the 2's come across, you'll see they are inside our original domain. We don't accept the second and third quadrants because that would give us a negative value, and we can't have a negative value, we need a positive half. Right, so it's always a bit hard when it's already pre-written out, so let's go through an example. Solve the equation for sine 2 theta is equal to half, for theta being between 0 and 2 pi. Well, first thing I'm going to find is my working domain. And to do that, I need to look at what is this thing inside the brackets. Well, in this case, g of x is equal to 2 theta. And I'm going to sub in the 2 endpoints of my original domain. So I get g of 0, and that happens to be 0. And g of 2 pi is equal to 2 times 2 pi. That's going to give me 4 pi. So I'm going to, my working domain is now 0 to 4 pi. So we had sine of 2 theta is equal to half. So 2 theta is going to be sine of what angles give me half? Sine of pi on 6 does. Pi on 6 gives me half. That's in the first quadrant. That's I put it here. That's my first allowable. And just to get the practice, let's find in the first, second, third, and fourth, and then we'll restrict them depending on sign. The second quadrant will be pi minus pi on 6. Third quadrant will be pi plus pi on 6 using those tables of symmetry, and then the fourth will be 2 pi minus pi on 6. Now we needed positive half though, so we only allow the quadrants where sine is positive, and that happens to be in the first and the second, so we get to rule off the third and the fourth. So those aren't allowed because sine's negative. The only thing is our working domain is from 0 to 4 pi, so not only are we allowed the first and the second, we could technically think about, well, 1, 2, 3, 4, that's going around once. I could go around again and call that the 5th, 6th, the 7th, and the 8th quadrants if I went one loop, and then I go a loop around again, because I'm allowed to go around in my working domain till 4 pi. So what quadrants in the second loop are positive? Well, that is the 5th and the 6th. So we're effectively just adding 2 pi to our initial solutions that worked, because I'm just going all the way around once, which is 2 pi, and then I'm just going back to the same positions. So this one here will be 2 pi plus pi on 6, and also 2 pi plus pi minus pi on 6. That whole thing there. So let's simplify these all down. So we get 2 theta is equal to pi on 6. Pi, take away pi on 6, is 5 pi on 6. 2 pi plus pi on 6 is 2 pi, the same as 12 pi on 6. So that'll be 13 pi on 6. And 3 pi is 18 minus 1 is 17. 17 pi on 6. The way I'm getting to those fractions quickly is the 2 pi, I'm converting that to, well, what's the 2 would be as a fraction over 6? Well, that's just 12 on 6 plus the 6 on 6 minus the 1 pi on 6. So 12 plus 6 is 18, take away the 1 is 17. So it's 17 pi on 6. But that's what 2 theta is. Theta is now equal to, divide all of those by 2, so we get pi on 12, 5 pi on 12, 13 pi on 12, 17 pi on 12. And you'll see those are all inside our original domain. So that's how we do that. If you're comfortable on this idea, find the working domain, solving, finding all the matching symmetrical quadrants that get the correct sign, then that's fine, and then it's just moving the 2 over, and you're probably pretty happy to go ahead and have a go at some problems. Otherwise, I've got one more example, and this one's a bit trickier, especially because g of x. So if you want to stick around, watch, otherwise have a go yourself. Right, so g of x in this case is equal to 2x plus 2 pi 3, we'll call it. So our working domain is going to be, we're going to do g of, and in this case we're starting with negative pi and pi, so put in negative pi and we get 2 pi plus 2 pi on 3, which is equal to negative 2 pi plus 2 pi on 3. So it's negative pi putting it in. That is going to work. Negative 6 plus 2, that's negative 4 pi on 3. And then g of pi is 2 pi plus 2 pi 3. 6 plus the 2 is equal to 8 pi on 3. So that's my working domain. So I need to accept any values between negative 4 pi on 3. So starting at 0, I actually need to go backwards this way. There's negative pi, and there's that's about negative 4 pi 3. And then I also need to accept any values that go around to 8 pi on 3, which is all the way around to 2 pi, and also around another 2 pi on 3, so back to here, to there. So a whole rotation and a bit more. So we've effectively got the negative 1 quadrant, negative 2 quadrant, a little bit of negative 3 quadrant. We've also got quadrants 1, 2, 3, 4, back around into 5, and a little bit of 6. So there's heaps and heaps of solutions that may work for this. So we have now got back to our original problem. Cos of 2x plus 2 pi on 3 is equal to negative half. So we need cos values. So yeah, an angle that gives us cos values negative half. So that's negative. That's negative, so that means it needs to be over in the 2 and 3. So we instantly get to rule off anything over here. anything there, because anything in those quadrants would be give us a positive cos value, or positive horizontal component, I should say. Right. So we're going to get 2x plus 2 pi on 3 is equal to, what's our first one that works? Is over in the second quadrant. That's going to be, well, if we thought of the first quadrant, let's write that because that's sort of our reference one, and that's going to help us find the other one. So if we did think in the first quadrant, so if we ignored the negative for now, gives us half for cos, that's the smallest, that will be pi on 3. Is that right? Yeah, that's right. Okay, so that's our first, so that's sort of our reference in the first quadrant. We're going to exclude that because it would technically be a positive one, but we'll just use it for now. So then we know in the second quadrant it's going to be pi minus pi on 3. We know in the third quadrant it's going to be pi plus pi on 3. We can exclude the fourth quadrant because it would technically be a positive cos value. We can exclude the fifth quadrant, so we exclude that fifth, and then we're coming around here into the sixth quadrant, so that's the same as 2 pi plus a whole nother pi to get round and then come back our reference angle, pi on 3. So that was all the positive quadrants. What about the negative quadrants? Well, that would also be back around to negative pi, but then plus pi on 3 would work. And then we would also have negative pi plus pi on 3. And that's it. That's everything. And then we're just going to ignore our actual reference one from in the first quadrant because that doesn't count. So they're all the ones that could work. So there's heaps of solutions here. So let's start simplifying those. Is equal to pi minus pi 3. Oh, not simplifying. Silly me. 2 pi on 3. That one. 4 pi on 3. So that's over there. So it's just a little bit out of alignment from the line above. But 2 pi plus pi is 3 pi. Take one is 8 pi on 3. Negative pi plus, that's negative 2 pi on 3. And then we also get, supposed to be a minus there. Negative pi, take another pi on 3 is negative 4 pi. Now this is where we should check because using our logic here and looking at geometrically up there, these should all technically be within inside our working domain. But let's double check. Nothing less than negative 4 pi on 3, well that's fine, and nothing greater than 8 pi on 3, so fine. And we get to include them because it was square brackets. So those all work, and now it's just a matter of moving everything on this left-hand side of the equation over and to get x by itself. So we get 2x is equal to, now we're going to do 2 pi. And we have to take this because we've got plus 2 pi on 3 here on the left-hand side. We have to take away 2 pi on 3. So we have to take that away from every one of those solutions. 2 pi on 3, we get 4 pi. Take away 2 pi on 3. 8 pi on 3, take away 3. Negative 2 pi on 3. 3. And I hope you're starting to realize that these problems have a lot of work in it. So if you're asked to sketch, and we're doing this just as a practice, we're assuming that this came about because originally this was maybe something equal to 0, and then we've rearranged and we've got the negative half because we were just trying to find intercepts. So this graph we're graphing, we have 1, 2, 3, for 5 intercepts. And that happens, that can certainly happen. So what do we get? 2x is equal to 0, 6 pi, negative 4, and 3. Now we're going to divide everything by 2 to move the 2, so we get x is equal to 0, 2 pi on 6, 6 pi on 6, negative 4 pi on 6, negative 6 pi on 6. Let's simplify those, so we get 0, pi on 3, 6 on 6 cancels, so we get pi, we get negative 2 pi on 3, and we get pi. And those are all inside our original domain, so that works. Last thing is you generally want to write them from smallest to largest. Just a really good habit, so we would actually start with the negative pi is the smallest, then negative 2 pi on 3, then 0, then pi on 3, then pi. And that's it. So lots of work. That was another 10 minutes there, but that's also me talking through the whole process. But I hope you're starting to really realize the importance of knowing your exact values off by heart, being able to think, is it asking for a horizontal component or is it asking for a vertical component? And if it is it asking for a positive or negative one of those? And then what quadrants will that actually work in? Is it quadrant 2 and 3 or 1 and 3 for 10, or who knows what it is? But you need to be able to work through all of that process just to get all of this right. And you'd be expected to do all of this just to get the intercepts of the graph. So heaps of work when it's CAS free. But there's almost always a sketcher, cos or sine, or even a tan graph, which we'll get to later in the tech free. Actually, yeah, pretty much always. So yeah, that's it for the video. If you have questions, please ask. There are now a couple of previous exam questions to show you what it is. So there's one, there's 2 marks. Need to solve for that. And so you hope it's not something like this with 5 solutions, but it could be, and that it could be the case for only 2 marks. So you need to be able to do that in 3 minutes. That was part A of it. And then part B is then sketch that graph, labeling endpoints, local minimum points with their coordinates. Part of that is realizing that in this case the amplitude's 2, but the whole graph has a k value of equal to 1, which we'll get to when we look at graphing in the next video. So it happens to be, this isn't exact, but we get that situation. So the intercepts are the minimum values that ask it, the local minimums, the lowest points. So it'll be some situation like that where the whole graph, its center has been moved up from around 0 up to 1. And because it's yeah, and oh no, that's wrong, because its amplitude is 2, so even though it's been moved up 1, it's going to be something like that, and drawn that down too far. Up. So you'd also need to find those minimum points by letting y equal to -1 and then solving the equation as well. So heaps of work in there. Yeah, but have a go. If you have questions, please ask in class or send an email or put a comment in the video below or something on Google Classroom. Happy to hear from any of you at any time. See you and have a good evening.